Okay, welcome back everyone to another video. Today we are talking about section 2.1, linear systems, and this will cover most of 2.1. I'm glossing over the solutions to linear systems because we're going to learn a more efficient way of doing it in section 2.2. And technically the way the book shows you, everyone learned in Algebra 1 and Algebra 2. So if you need a refresher on that, it is in the book in section 2.1. However, except for some basic problems on the WebAssign, we're going to skip right past it to learn about Gaussian elimination in the next section. Okay, so a linear equation of n variables has the form ax or a1x1 plus a2x2 and so on plus anxn equals b, where a1 through an and b are constants. So note that all equations that contain powers, so like x squared, y cubed, things like that, trig functions, sine of x, cosine of y, right? Logarithmic functions, exponential components, right? Or exponential functions, so anything like e to the x, e to the xy, e to the x2, these are all nonlinear. So linear just have the same form, right? A scalar times a first order variable, and then we're just adding and subtracting them, no multiplication. So some examples of linear equations: 4x plus y over 2 equals 7, e squared x1 plus 5x2 minus pi x3 equals 0, and x1 minus 3x2 equals x3. Right, so some things that I wanted to kind of emphasize here, right, are notice that e squared and negative pi. So a lot of times people act like these transcendental constants aren't constants. So if you see things like the square root of e squared, sine of pi, something like that, then we feel like, some people feel like they're not linear, but all we're concerned about is functions of our variables, x1, x2, xn, and so on. So some nonlinear would be 3xy plus z equals 6, right? Because this multiplication part here, and 4 times x1 squared minus e to the x2 plus the natural log of x3 equals 8. Right, so there's a number of reasons here why this is nonlinear. We're only going to be dealing with linear systems in this course. So speaking of linear systems, a system of linear equations is a finite set of linear equations. A solution to the linear system is a vector that is simultaneously a solution of every equation in the system. Right, so if we have a set of answers, so x1, x2, x3, x and y, that's a solution to every system. This is just more formally stating what we've always thought about solutions to systems, except for the part where it's a vector. So suppose that we have a system of equations. So I say 4x1 plus 3x2 equals b1, x1 minus 2x2 equals b2, and I have a linear combination of vectors, right? So c1 times 4, 1 plus c2 times 3, negative 2 equals b1, b2. Right, so we saw in one of the tasks in class that these are going to have the same solutions, right? In fact, the way that it was often approached was, if I gave you a vector equation, right, then we could convert it into a system of equations to solve. Right. The idea being that these are going to have the exact same solutions, right? So x1 would be c1, x2 equals c2, and often you'll just use the same variables, right? So there's nothing special about using c or x. It's just in those contexts you often see them like that, but the letters really don't matter. It's the idea of that scalar. But notice that this looks just like the components of its own vector, right? So x1, x2 equals c1, c2, and this is really what we're getting at when we talk about a vector that's a solution. And we'll see more of this in the next section. We kind of touch on the idea of how these relate to matrix equations, and you'll see kind of the vector being the solution to that. All right. A linear system, right, has three possibilities for solutions, right? So it can either have a unique solution, so exactly one, it can have infinitely many solutions, or it can have no solutions. And so if we have any of these, then right, we call these consistent, right? So a consistent system is just a system that has any solutions, right? One or infinitely many. Right? A system with no solutions is called inconsistent. So if we're talking about a consistent system, then it just means there is at least one solution. Okay, so kind of some examples in R2, right? So if I'm thinking about systems of equations where, say, this is a graph of an equation, that's the graph of an equation, then this system would have a unique solution, right? A single x1 and x2. This system, so suppose I have one equation and then another equation, and they both fall exactly on the same line, right? So you can imagine that I've got another line here, right? And they both fall on the exact same line. So there's going to be infinite solutions, right? There is an infinite number of places where x1 and x2 solve this system, right? Because if I'm thinking about a solution to a system, it's where both these lines are covering the same point. If they're the same line, then that happens an infinite number of times. If the lines are parallel, then that would be no solution, an inconsistent system. Right? And so in vectors, we kind of saw how these things are related. Right? Vectors that would give me a unique solution would be, say, right, linearly independent vectors, vectors that point in different directions. Right? So u and v cover all of R2, and any point that I wanted to get to, I would get to with a unique combination of u and v. We showed that in class. Right? An infinite number of solutions, right? So u and v, if they're scalar multiples of each other, if I'm just looking at two of them, then we saw that they might lie on the exact same line. And if I'm trying to figure out how to get to a point that lies on that line, then there's an infinite number of solutions that would get me there. Right, so if I have 2u minus v gets me to this point, then likewise 4u minus 2v, and so on. So there's an infinite number of, for any points that are on this line, I'm going to be able to have an infinite number of combinations of u and v that would get me to that point on the line. Right? Whereas if I'm looking at something off the line, well, the whole point of this was that we can't get everywhere in R2. Right? So if there's something that's off the line of u and v, then I'm never going to reach it, right? And that's kind of showing here. Like if I have this set up, then this might be like where I'm trying to get to, and I'm never going to be able to get there. So we're going to spend more time on showing how these things are related. A good chunk of section, or unit 1, is built around kind of connecting the ideas of vector equations, systems of equations, and how we get information from one and compare it. In that vein, another way to represent a system of equations is with an augmented matrix. So I'm just kind of showing by example because I think it's more helpful than a formal definition. So if I take the augmented matrix of a system, essentially the numbers that are formed in my matrix, right, are the coefficients of the corresponding variables in my system, right? So you can kind of think of the way that I'm forming the matrix, right, is the line for the augmented part is coming down here along the equal sign. and then I've got this like so. Right, so for x1, my coefficients are 3, 1, and 1/2, right? Now, so like this is, you could kind of think of this as my x1 column, right? This is like my x2 column, like my x3 column, and so on. And so one thing to kind of be careful about, and just often you can forget, is there's no x2 up here, right? So that doesn't mean that we can't make an augmented matrix. Anytime you don't have a variable, then the implied coefficient is 0, right? So if I wanted to write this out, this is really 3x1 plus 0x2 plus x3 minus 2x4. And of course, we would never write 0x2 necessarily when we're writing a system of equations, but this is what shows up here, right? So that's, if you're converting a system into an augmented matrix, then anytime you don't have a variable, remember to put down the 0. So we'll see next time in the next video why having an augmented matrix is so helpful. But most of the time we're actually going to be working with the augmented matrices because they're much more straightforward to work with. So what we want to kind of get comfortable doing right now is getting to where seeing this thing gives us exactly the same sort of information, and we can recognize that all the information we're getting from here is going to kind of be just as clear as what we could get from this. So that's where we're heading. That's it for 2.1. Have a nice afternoon, everyone, or evening. I will see you in class.